पॉज हे करू ना
नाही पॉजची गरज नाही ते केलं चालेल
आता रन कर Very good evening from India and very good morning in California Pacific time. Friends, welcome to World Space Week second day's program of Nashik India chapter. We have a very eminent speaker today, John C Mankins, who is the president of Artemis Innovation Management Solutions LLC and also a director of National Space Society. Friends, before we start, for the kind attention of the viewers, let us follow certain etiquettes while watching the live program. Be in a quiet room or disturbance-free location. Turn off your camera, please. Video stop. Please remain muted. Otherwise, the background noise will be heard by all the attendees. Use chat window to ask your questions. Be respectful of the speakers and other attendees. Please note that this program is being streamed live on NSS Nashik India chapter YouTube link. Please use that. Our today's program agenda: introduction of World Space Week, introduction of the National Space Society, introduction of NSS Nashik India chapter, introduction of the speaker, then presentation by the speaker, and if time permits, we'll go for question answer session and then announcement for tomorrow's program. What is World Space Week? The United Nations General Assembly declared 4th to 10th October as World Space Week to celebrate each year at the international level for the contributions of space science and technology to the betterment of the human condition. Every year there is a different theme. This year, 2020 theme is Satellites Improve Life. These dates commemorate two events. What is the importance of 4th October and what is the importance of the 10th October? On 4th October 1957, launch of the first human-made Earth satellite, T1, thus opening the way for space exploration. October 10, 1967 is the signing of the treaty on principles governing the activities of states in the exploration and uses of outer space, including the other moon and other celestial bodies. Now about National Space Society, NSS. NSS is an independent educational grassroots non-profit organization dedicated to the creation of a spacefaring civilization. It was founded as the National Space Institute 1974 and L5 Society 1975, which merged to form National Space Society in 1987. NSS is widely acknowledged as the preeminent citizen's voice on space. NSS has several chapters in the United States and around the world. Its headquarters is located at Washington, D.C. The society also publishes Astra magazine, an award-winning periodical. The most important development, space. What NSS does for education? It has a tremendous program for students and academia. All the information is given on the website of the National Space Society, which is space.nss.org. NSS membership categories. NSS associate membership is just $5 US per year. Regular individual basic membership is $45 per year. Individual senior membership above 60 years is $35 per year. Student individual basic membership is $25 per year. Member benefits are also available on the website of the NSS. How to join NSS? Just visit NSS website and follow the instructions to continue till the payment. Nashik India Chapter. It was inaugurated on 26 February 2016 by India's eminent nuclear scientist Padma Vibhushan, Dr. Anil Kakodkar. And these are the present office bearers. This is how it was inaugurated. In just existence of 4 years of Nashik India chapter, our chapter has received 3 consecutive year awards for our activities. The Excellence Award presented at ISH 2018 in Los Angeles. Then Special Merit Award presented at ISH 2019 in Arlington, Virginia, near Washington, D.C. Then Special Merit Dunlop International Award for activity in 2019 online program. Our chapter had a great opportunity to felicitate in a typical Indian cultural style to the NSS leadership in Los Angeles at ISDC 2018. And I'm so happy to tell you the fourth from the left, fourth from the right, just who is sitting just near me is our today's speaker, John Mankins.
Of the dais, I would like to felicitate all of you as a second human being.
मी नाही करणार मला करू द्या आता.
We had the lifetime opportunity to felicitate Dr. Buzz Aldrin, the second human being to land on the moon. I also had the lifetime opportunity to have a meeting with Buzz for 35 minutes. Last year, I had an opportunity to talk to and meet Jim Bridenstine, the NASA administrator. Friends, now what is the program agenda for today? Our program agenda for today is our speaker, the most eminent speaker, John C. Mankins, who is the president of Artemis Innovation Management Solutions LLC, and he is also a director, National Space Society. Subject of presentation is lunar exploration, development, and settlement. Now, let me take this opportunity and privilege to introduce our eminent speaker. John C. Mankins is an internationally recognized leader in space systems and technology innovation. Innovation is a key word for John. And as a highly effective manager of large-scale technology R&D programs, Mr. Mankins is an accomplished communicator, including political, programmatic, technical, and lay offices. He has authored or co-authored more than 80 published papers, reports, and other technical documents, and has testified before Congress on several occasions and has been consulted on R&D management and space issues with organizations in the US and internationally. Mr. Mankins' 25-year career at NASA and Caltech's Jet Propulsion Laboratory, JPL, ranged from flight projects and space mission operations to system-level innovation and advanced technology research and development management. He is also well known as an innovator in R&D management. For example, building on the original NASA Technology Readiness Level, which is TRL, Scale for Technology Assessment, defined first with 6 or 7 levels in the 1970s. He extended the scale to flight systems and operations in the late 1980s, that is TRLs 8 and 9, published the first edition of the TRLs in 1995, and promoted the use of the scale by the US Department of Defense in the late 1990s. Before leaving NASA, Mr. Mankins was the manager of exploration systems, research and technology within the Exploration Systems Mission Directorate with responsibility for $800 million annual budget, involving more than 100 individual projects and over 3,000 personnel. For 10 years, he was manager of advanced concept studies at NASA and the lead for critical studies of space solar power, highly reusable space transportation, affordable human exploration approaches, and other topics. He was the creator or co-creator of numerous novel concepts, including the MagLifter, electromagnetic launch assist system, the internet-based NASA Virtual Research Center, the Solar Clipper, interplanetary transport vehicle, the Sun Tower space solar power system, the hybrid propellant module for in-space refueling, the Habitable mobile planetary outpost architecture, the advanced technology life cycle analysis system, Atlas, and others. He holds undergraduate Harvey Mudd College and graduate UCLA degree in physics and an MBA in public policy analysis, the Drucker School at Claremont Graduate University. Mr. Mankins is a member of the International Academy of Astronautics, IAA, and chair of the Academy Commission 3, Space Systems and Technology Development, and a member of the International Astronautical Federation, IAF, the American Institute of Aeronautics and Astronautics, AIA, and the Sigma 11 Research. In recognition of his accomplishments, he received numerous awards and honors, including the most prestigious NASA Exceptional Technology Achievement Medal, of which he was the first recipient. Started from him and for him. So, let us welcome our most eminent speaker, John Mankins. Over to you, sir. Please take over and start your presentation.
Avinash, thank you so much. A very early good morning to you and to all of the participants in India and elsewhere. It is a great pleasure to be with you today to speak at this World Space Week event about the future exploration, development, and settlement of our moon. I hope everyone can hear me okay. It's okay?
Yeah.
Thank you.
Yeah.
So this morning, let me bring up my screen. Very good. So this morning, the emphasis on my remarks will be on the farther term opportunities that the moon represents for humanity. The focus will be on a set of studies that are being done by the Moon Village Association, which is a partner organization with the National Space Society. Just a few years ago, there were relatively few missions going to the moon. Between 2001 and 2015, only about 10 missions, one of which was the Chandrayaan-1 orbiter and impactor, along with several Chinese missions, US missions, and the Kaguya Japanese mission. And because of what these probes and orbiters discovered, this is what the planning and missions for the moon look like now. Instead of 1 or 2 missions every 2 or 3 years, there is a swarm of programs missions, orbiters, landers, CubeSats, sample returns, all planned and leading within the next few years to a human return to the moon. And it is anticipated that India will continue to play a significant role in these activities, along with 8 other countries, all of which are sending landers, probes, orbiters, etc., to the lunar surface. Why are they doing this? Well, one thing that the earlier missions discovered is that the lunar south polar region, the south pole of the moon, as well as the north pole of the moon, are in fact extremely cold. This is the peak temperature data, just to show you. So this is the peak. The peak is around 0 degrees Celsius, and the minimum is approximately 230 degrees below 0 Celsius, so about 40 degrees Kelvin. And because of this, what was discovered in the last 15 years is that there is significant water ice at the poles of the moon. Water ice has significant potential value to be used both for life support systems, for water for an outpost or a settlement, but also it can be cracked using electrolysis into oxygen and hydrogen and turned into rocket engine fuel. And if you have the opportunity to make fuel and life support materials locally, then it is not necessary to bring everything from the Earth. And there's a great deal of promise in these resources for the future. So now I will talk to you. So that's the background, and that's the reason why so many countries are involved in going to the moon right now. I'd like to speak with you about the case study that is being done by the Moon Village Association and begin with the conceptual framework for this study. So this is the framework involves the consideration of several potential scenarios for the future, organizing information into a set of elements within a taxonomy, and then to identify key building blocks from within the many prospective parts of a Moon Village activity. So it is impossible to know the future with certainty. However, there is a very strong technique called scenario-based planning, which was developed 50 years ago. And the core idea is that although you cannot know the exact future, you can identify the major options that might happen in the future, and then look at the combination of these options to see what a prospective future could be. Now, scenario alpha that we are looking at presupposes that the future for the moon will be similar to the events of the past in Earth orbit, things such as the International Space Station, and that human spaceflight programs will drive lunar surface activities. The second scenario is scenario beta, and in this case, the assumption is that government science programs will drive lunar surface activities in the same way that science activities drive the activities of various governments in Antarctica. And lastly, scenario gamma, it presupposes that private ventures will drive lunar surface activities. I show you these just very briefly. Each of the scenarios has defined timelines driven by in the case of alpha, human spaceflight goals and objectives. In the case of scenario beta, driven by science goals and objectives, and in the case of gamma, driven by opportunities that are made possible by ongoing innovation and investment in the private sector. So of course, none of these three is exactly the future. However, the concept is that all three of these will weave together like a three-stranded DNA molecule to form our future vis-a-vis the moon. Within this framework, we have the taxonomy that I mentioned, the architectural elements, which range across 5 major categories: Earth-based operations and activities, mission and market-related operations and activities, orbital systems, surface systems, and transportation systems. Each of these are very much like the taxonomy that one finds for natural systems, such as kingdom, phylum, class, and so on. And the idea is to provide as I said, to provide a framework for organizing information about the very wide variety of system concepts, capabilities, software, interactions, and so on among these various types of systems related to the moon. And then from those specific high-level categories, there are also candidate potential prospective building blocks, systems that fall within each of those categories and which might be developed over the coming years. And I'll speak much more about those in a few moments. So with regard to our specific architectural studies, this is a case study that we are now undertaking. It's focused on the south pole of the moon. There's a series, we have defined a series of zones within which we anticipate activities will take place. Zone 1 and Zone 2 at the south pole of the moon, Zone 3 for science on the far side of the moon, low lunar orbit, Zone 4, cislunar space, including the libration points, Zone 5, and Earth orbit, Zone 6. Within each of the zones, we have identified a variety of candidate kinds of systems that fall within the architectural elements. And we've done this in 3 time frames, so as to get a snapshot over time of how the moon might develop and change, starting in about 5 years. So in 2025, then in 15 years, 2035, and in 25 years, 2045. And it's 2045 that is the principal focus of our studies right now, because by focusing, if we focus too close, then there's a constant churn as government programs are changed and budgets are approved or disapproved as new discoveries are made. And so as our role as a non-governmental organization, we believe, is to help guide and inform activities that are targeting on the longer term. So activities that have to do with education, that have to do with creating new technologies, that have to do with creating new business opportunities. And the governments will do what the governments will do. It's not our concern to try to tell governments what they should pursue. In looking at 2045 and thinking about the future over the next 25 years, we realized last winter, in the context of the Moon Village Association workshop in Tokyo, that there were several important activities right now going on which inform the course of the future. Probably the single most important transformation which has happened in the last several years is the emergence of very low cost access to space. 20 years ago, it was a law of nature almost that the cost of access to space was approximately $20,000 per kilogram US dollars. Whereas today, because of SpaceX, the Falcon 9 reusable launcher, and the coming systems from SpaceX, the Starship, and the new launcher from Blue Origin, the New Glenn launcher, and other launchers which are now being planned in Europe and in China, in various places, we believe it is the cost of launch will be between $1,000 and $2,000 per kilogram within the next 10 years. And so this is a key assumption for the study that we are now undertaking. Right now, the cost of launch is on the order for the Falcon 9 reusable is listed as being approximately $2,500 per kilogram. This is already almost a factor of 10 reduction below the standard cost only 10, 15 years ago. So because of this, because of the advent of low cost for access to space, massive new mission opportunities and commercial markets are becoming possible. And the most significant of these is already unfolding. And again, it's with SpaceX, but it's generic to everyone. And this is the idea of space-based global internet connectivity. If you look at the Starlink system, if you look at the Kuiper system, if you look at concepts like OneWeb and so on, all of these are going to put into place massive low Earth orbit constellations for communication. The most important aspect of this, other than the commercial opportunity and because of the connectivity, is the radical change in the production of space systems and space hardware. In particular, right now, SpaceX for the Starlink constellation is fabricating approximately 30 tons of flight qualified hardware, 700 kilowatts of space solar power systems every month, and launching them for its constellation. This change to go from once in a while, every so often, to tons of flight hardware on a production line every month is going to lead to affordable megawatt power everywhere in cislunar space. And when we have power in near Earth space in megawatts at a cheap price, it means that the physical resources of space can then be developed. And if the physical resources of the moon are developed effectively, then a sustainable permanent human presence becomes affordable. So this is the line of thought. It starts with low cost launch, and then it proceeds through the mass production of affordable energy systems to resources to humanity. So our focus, as I mentioned, was on 2045. We've got the major emphasis is on zone 1 and zone 2 at the South Poles. And because of our assumptions, we believe now that, and we are studying the idea that by 2045, within 25 years, that the first self-sufficient permanent human settlement could be established on the lunar surface. This is a rough functional block diagram of such a settlement. It includes the major elements for inputs and outputs within which we frame our studies and the identification of the building blocks, which I'll describe in a moment. I wanted to just take a second and remind you of what the South Pole of the moon looks like. This is our focus. The South Pole of the moon is dark and cold. And that's the principal reason why the ice, which is of great interest, is there. And so, but there are locations, for example, near the exact South Pole of the moon, where there are ridge lines that are very frequently illuminated, and therefore are significantly warmer and have adequate energy to allow human activities. And they are very close. The Shackleton crater is about 20 kilometers in diameter. And within the illuminated ridgelines, within just 10 kilometers or 15 kilometers of these illuminated ridgelines, there are the permanently shadowed regions where the ices are deposited. So in terms of the lunar settlement, it's the requirements for a lunar settlement. Basically, the core requirement is it has to be somewhere that you can get to and return from vis-a-vis the Earth. So there must be locations for safe vehicle landing and ascent. There have to be energy flows. You have to be able to get solar energy. Nuclear energy, of course, is of interest and has strong potential for specific applications. But nuclear energy is time-consuming. The development of the systems is time-consuming, and it can be highly problematic for launch and expensive. And so it's very limited in terms of its utility for lunar development and settlement. An interesting requirement, the moon, if you go back and I'll take a moment and just look at this. If you zoom in on these locations, and I'll show you more of that in just a moment, they can be extremely rough terrain. We get the feeling that the moon is a smooth place because of the locations that we've all seen the pictures of from the Apollo moon landings 50 years ago. However, much of the moon is extremely rugged, especially at the lunar poles. And so it's very important for the concept of operations, CONOPS, that the surface in the vicinity of a settlement must be smooth enough for mobility in the vicinity of the settlement, and in particular to reach the volatiles, the ices. Biological requirements for a settlement. This is just a handful of them. Obviously, air, water, food, but also there must be self-sufficiency. We have to be able to have the chemistry and the biological systems for recycling of waste, for agriculture, for dealing with personal requirements. There has to be adequate lighting and energy, not just for the systems, but also for the inhabitants. And of course, there must be key systems like EVA systems, that's spacesuits and mobility systems and so on for repair and maintenance. There must be communications. All of these things are required. There are also tertiary requirements. For example, we believe that it is not possible to contemplate a settlement in which all of the materials are brought from Earth. It's necessary for a settlement to be a living thing. It must be able to ingest from the local environment. It must be able to grow, to make air, to make soil, to extract and to use the local water. And it must do that to the greatest extent possible, independently of imports from Earth, which even with lower cost transportation will continue to be prohibitively expensive. It's impossible to establish a small biosphere away from our planet by bringing everything with us from our planet. And of course, we believe that in the nearer term, that one of the economic opportunities for such a settlement would be to support and to allow public space travel and tourism for people to come to the moon. This is a map of the from the Lunar Reconnaissance Orbiter, Lunar Orbiter Laser Altimeter, which is a derivative of from the LRO mission that provides the slopes. And I just wanted to show you here the slope on Shackleton Crater in the red. This is on the approximately 40-degree slopes. So if you look outside, if you make a 40-degree slope, it's like that, and it's a rough terrain. It's steeper than a very aggressive hill for skiing or something like that, or winter sports, and very poor in terms of prospective mobility. And so the location that we've looked at for a potential settlement is not at the rim of Shackleton Crater, but rather is over on this ridge line to the left of the red circle Shackleton, where there are reasonably smooth locations and good prospects for addressing the lunar resources. In terms of biological requirements, we've looked at in some detail over the last several years at what it would take to have a biologically self-sufficient settlement. Obviously, human beings cannot live by themselves. We survive only because we live in concert and in harmony with thousands of microbes and fungi and viruses that live inside of us, and thousands of fungi and bacteria and plants and insects that live with us. And so there must be some ecological balance. We have identified approximately 40 settlers, 40 people to be a sort of a de minimis, a minimum amount of number of people, biologically independent individuals, and that in order to live you essentially need something like 1,500 square meters per person. And so these numbers just identify the overall requirements for 40 people to live away from the Earth or to live on the Earth. And probably the single biggest parameter to keep in mind is the amount of soil, air, and energy that are necessary for people to be able to live, to be able to have agriculture and their food, and to recycle their wastes. And this is a tremendous gift that we get for free here on Earth. The sun just comes down, but in space, we have to provide it and provide for it. And this is one of the reasons why these advances that I mentioned in production of space solar power systems are so critical to enabling a settlement within the next 25 years. So in terms of our concept, we're still looking at a wide variety of the details. One of the issues, of course, as I mentioned, was mobility. The images on the left just show a couple of old, what are called rovers, the Apollo rover, of course, and one of the Mars rovers. I will confess, I personally have a bias toward nature. Natural systems have very few wheels. They do have a great many legs. And I think legs will be quite important to be able to have good mobility with the steep slopes that exist at the south pole of the moon. Another challenge is energy. This image is a topological map. The dark orange is almost 2,000 meters, 2 kilometers above the average altitude of the moon, whereas the violet, the pale purple, is almost 3,000 meters below the average. So, and the distances here, as shown, is you can see the scale for about 25 kilometers. And so what you see is that over very short distances, like 10 kilometers from one point to another, that you can have variations in elevation of 5 kilometers. And this kind of variation in those kind of distances are just, they're very hard to envision. It's like the kind of scale in changes in elevation over short distances that you see at the Grand Canyon in the American Southwest. It's really stupendous geological features. I mentioned the functional diagram a little while ago, and the idea of these biospheres. Obviously, within a biosphere, there are a variety of interactions between the soil, the living organisms that make up the soil and provide the recycling and the food and everything else, the humans, the major inputs, including air, water, and energy, and of course, the various mechanical systems that will be necessary as well. But one level down, there are a wide variety of other interactions that we have to understand, that we have to be able to model, that we have to be able to develop. Building a small biosphere on the moon will require a much greater understanding of all of the natural systems of the Earth than we have now. There's the whole question of habitable volume. These are several different concepts for how one might build a volume on the moon. The one on the far left is a very typical sort of space station-like module. The one that's in the middle is a more recent European concept of building, bringing from Earth a series of modules. And then there's the idea of building a very large dome. Our feeling is that none of these is appropriate for a settlement in the next 25 years. And in fact, what we're looking at is how one might build a settlement using lunar regolith, the lunar materials, to essentially print habitable volume, just like the inhabitants, the Anasazi people of the American Southwest have, over the last 1,500 years, built settlements out of the living rock and local clay in Arizona and in New Mexico. And of course, there are similar settlements in a wide variety of locations around the world, places that have been carved out of the living rock. I like this one very much because of the scale. This is about 100 people, and because it's quite similar in its appearance to the kinds of locations that are available at the South Polar region of the moon. We have selected a couple of sites as the candidates for our current studies. They're highlighted here in this version of the terrain map. This is a close-up. Those two craters, you can see them here. There's two craters. This is a typo, I apologize. The scale of these craters is actually about 800 meters. And the idea is that these two locations represent a very promising site for lunar settlement. And I might just mention, going back to this image, that if you look at this picture and you think about where it is on the moon, it's almost exactly at the south pole of the moon. And the moon is tidally locked with the Earth, so the same side always faces the Earth, as you know. And if you're at the South Pole, the Earth itself hangs in the sky, always, if you can see it, hangs in the sky in the same place basically forever, while the sun moves around the Earth, around the moon, as the moon, actually the moon moves in its orbit around the Earth. So the moon's orbit is about 27.5 days, and its rotation is the same 27.5 days. So in fact, in these, from these locations, the Earth would be hanging in the sky just at the top of the image. So from these two craters, if you were standing on the rim here, what you would see looking out and up to the top of the page to approximately the L would be the enormous, beautiful Earth hanging in the sky. And we think this is an extremely promising location to consider for the first human settlement, so that everyone could always still see the Earth and feel close to home. I mentioned several times the building blocks. I'd like to just take a couple of minutes and go through these. Essentially, these are things that are needed in order for a settlement to be realized. Again, all of the programs are ongoing, all of the activities of the various governments and so on, but it's important to think about the longer term, take a position 25 years from now, and then look back toward the future. And these are all the capabilities, things like local construction, the dealing with waste, both physical and biological, agricultural systems, EVA systems, robotic systems, networks, computing, energy, all of these things will be needed for a settlement. And most of these new capabilities are not part of the current set of tools and capabilities of the aerospace industry internationally. You don't need biological waste processing on the International Space Station. You don't need lunar regolith processing or mining or on the International Space Station. There's no need for GPS inside the space station, and so on and so on and so on. So all of these are new capabilities and ones that we within the Moon Village Association believe are opportunities for individuals, for young people, for companies, for universities all around the world to become involved in their research, their development, and their realization. Just very quickly, obviously communications and networks is quite critical. We are watching avidly the efforts of, for example, the Space Communications and Networks Organization at NASA, developing protocols for internet for the moon. Energy and energy systems will be quite critical, as I mentioned, in these permanently shadowed regions. They are, for example, 10 kilometers away and 5 kilometers down. We think that wireless power transmission from the illuminated regions could be quite critical to getting energy down into these permanently shadowed locations. We've already talked about low-cost transportation into space, but in addition, there's a wide range of vehicles required for transportation from point to point in space, from space to the surface, for future transportation of products from the lunar surface back into space, and so on. Operations is a key building block. I put together this slide just to highlight the progress that's been made in the last 45 years. The drawing is from a report from 1980. It illustrates the idea of a lunar factory that could be self-replicating. At that time, using those technologies, this vision of a lunar surface factory was the size of a city. This was the scale that was believed to be required. And of course, today on the far left, with the yellow background, you see a typical 3D printer capable of printing fully functional robotic systems. And very soon we believe it will be capable of replicating themselves, just as, and that's why I put in the bees, there's no reason to have a city scale object to grow, to replicate, and to process waste, do manufacturing, and so on. All of these things these days can be done with far, far smaller systems. And of course, there's the whole idea of the resources, which it starts with orbital sensors and the surface instruments, but includes all the mining and processing and all of those things. And again, the illustration on the far right shows a vision from 1988 of lunar mining that was like terrestrial mining. This is almost certainly the wrong vision. Almost certainly today, given advances in robotics, given the progress in 3D printing, all of those things, the right metaphor is ants and natural systems that are much smaller and on a human scale to accomplish these objectives. And of course, there's the need to make habitation systems and self-sustaining biospheres, and I've already spoken about that at some length. An interesting question is that of spacesuits. Spacesuits are extremely expensive systems today, and in point of fact, if humans are going to live on the moon, and there are going to be scores of them, they cannot be dependent on spacesuits that cost $100 million. You'll have to be able to make space systems, airlocks, suits, medical systems on the moon. And so there's a real need to figure out how to make these systems far more effectively and in a far more modular fashion, so that they are compatible with a growing population on the lunar surface. And of course, robotic systems are critical in today's society, and this will certainly be true on the lunar surface. And not to neglect, science will play a key role, even if resources are quite important, and it will include the science of the moon. The moon is a record of the history of our solar system. Science from the moon, including astrophysics, radio astronomy, and science on the moon, including laboratory sciences that cannot be done conveniently or safely on Earth. I include here just a brief summary of some of the ideas on lunar settlement economics. Obviously, a settlement has to be able to survive economically as well as physically. And so it has to provide goods and services to government activities from various governments. It would need to provide, it would need to contract with commercial firms, both on the moon, but especially on Earth. And it would have to be able to provide goods and services to private individuals, people who were going to the moon to work and to live. This matrix is too complex, but I just wanted to give you a feeling for the kinds of goods and commodities and services that we're looking at, and the kinds of customers like government missions or like universities that would be the customers for these goods and services. And this just is as another way to look at that. And I apologize for too many slides on this subject. So, in summary, it certainly is. We believe there are going to be a lot of prospects. We think that the development of a settlement will be organic over a 10 or 15-year period, beginning in the early 2030s, in about 10 years, until there is an actual settlement, which is a thriving enterprise circa 25 years from now. And we believe that there will be an evolving set of opportunities for young people and for companies, new companies coming into the development and realization of lunar activities. There will, of course, be a wide variety of very critical interfaces and standards to assure interoperability. These include, for example, the lunar internet that I mentioned previously, but also systems such as propellants and life support. It makes no sense at all to have one habitat system with one kind of air and then another one with a different kind of air, so that the two are not interoperable. You can't go from one to the other safely and quickly in case of emergency. So there's a need to think about all of these things over the next 5 or 10 years to assure that the right design choices are being made in working towards the future. And I'll just close by saying that the Moon Village Association and the Moon Village Architecture Working Group, which I co-chair with Yoshifumi Inetani Sensei from Japan, that we are continuing our studies over the next several months and going into next year. And if some of you who are watching today would like to get involved in these study activities, please do try to join and get involved. We would welcome your participation. So thank you so much.
So, thank you very, very much, John.
It was my pleasure.
Yeah. Thank you very much for such an interesting presentation. Actually, one time I was feeling that I am actually walking on the moon, but was also afraid that I may skid down or I may slip down because of the slope, or I may get immersed in the water on the South Pole, but due to darkness, I may not be able to find it. And also, there are many aspects which we were not aware of, at least I was not aware of, about what the settlement is going to be. And actually, I'm so amazed to see that in 2045, where the moon settlement is going to come has already been planned and thought of. What a great, great work being done by space scientists all over the world, and particularly people like you. Thank you so much. There are not many questions. There is one question is, uh, see, the moon's gravity is 1/6 of the Earth's gravity. So will it be advantageous for manufacturing because of that gravity, or disadvantageous?
So I think the answer will be, of course, both. But also, please don't neglect that in addition to the relatively low gravity on the moon, there is also the easy availability of very strong vacuum. And in many industrial manufacturing processes, vacuum is a very fine thing. Now, 1/6G is going to be a very significant advantage in that there will be a direction for convection and for bubbles, but they will be, of course, slower, and the convection will be less effective in transferring heat because of the lower gravity. So I think it'll be very interesting. Of course, the virtue with the moon is because you do have a low gravity but not zero gravity, you can operate far more normally in a laboratory setting. And if you need a 1/2 G, you can still set up a centrifuge and make a 1/2 G. Or if you need 1 G or you need 10 G, you can, the difficulty on Earth is it's easy to make 10 G, but you can't go below 1 G except in a parabolic aircraft.
Yeah, thanks. There is another question. What is going to be our next home, moon or Mars or any other asteroid or whatever it is?
Yeah, so this is one of the big questions, especially for the National Space Society, which has been thinking about this for decades. I will freely confess that my own feeling is that the moon is exceedingly convenient and only 3 days away. And now that it has been confirmed that there is water, and that we already knew there was availability of energy, that there is a very, it's both convenient and there's energy and there's water. So I think maybe the moon. But Mars is extremely interesting from the standpoint of the chemistry and the vision and the imagination, but it is 9 months away. And so, and the sunlight at Mars is only about 35–40% of the sunlight at Earth. And so it's a very challenging environment for contemplating how you will do architecture to get you agriculture. Sometimes you see greenhouses on Mars. As far as I believe, this is impossible because the amount of sunlight is only like a pale dawn, just a very, very pale light, 590 watts per square meter at Mars orbit, as opposed to 1400 watts per square meter at Earth orbit. So, but this is a big point for discussion. But my personal belief is that the moon is next because it's easy, it has water, and it has energy.
Yeah, it is just like going from India to USA. It takes 24 hours. So going to the moon from Earth is just 3 days. So that is most convenient as far as transportation is concerned. Yeah, the next question is, do we require anti-gravity accommodation at moon? If it is so, then how can we design such colonies? Because the properties and parameters of the moon of gravity, radiation, environment, water, and all other things. So whether all the time people will have to be in the space suit, or the colonies would be under particular controlled conditions, then only they can survive.
Yeah, so it certainly it will always be necessary to live to be inside a habitable volume, a container that holds the air that we must breathe. If you're outside, you will need a spacesuit, of course. Another significant issue, which still must be answered by science, is what is the sensitivity of the human body to partial gravity. We have huge amounts of information, 10,000 years of information in 1G. We have 10 years, 20 years of information in 0G. And we have no information at 1/6 G. And so we still have to resolve a wide range of issues. And the same thing will be true for Mars or any other location in the solar system. We have to determine whether or not the human body needs a treatment, like maybe some time in a centrifuge, or some time every day with exercise, or if 1/6 G is enough to trigger positive physiological responses, so that we don't get the crippling bone demineralization that is observed in 0G, and nobody knows. So this is one of the major scientific research challenges that must be answered. But one of the best places to answer that question is on the moon.
Thank you. Of course, there is one interesting question, but maybe difficult. Why our target is moon? Why not K2 18b planet? Because at least acquire 50% of light speed until 2030, we are going to achieve, or what?
I don't fully understand the question, but
I have also not followed what exactly the question is. On what part of the moon these settlements would be? Because you have already made 6 zones on the moon, different parts of the moon, north zone, north pole, south pole, availability of water, and other things. So which would be the best location for the initial or the first settlement of the moon?
yeah, and so there are, of course, a variety of locations that might be chosen. The location that I showed in my presentation is a specific ridge, which is quite near to Shackleton Crater, within about 15 kilometers of the exact south pole of the moon. And that location has been chosen because it is very convenient for energy. It's convenient to get to the ice. It's convenient because of the smoothness, and also because the specific location has what we believe will be a very beautiful view of the Earth in the sky from the settlement. If you put it 10 kilometers away on the other side of the hill, then you will spend all of your time not able to see the Earth. And I think for the human soul, if you're going to live in a distant place, it's very important to be able to see home.
Will there be a situation in coming, say, 50 years or 100 years or so, that how easily the mobility of the humankind would be on the moon or on the Mars, just similar to the mobility and living on the Earth?
Yeah, so certainly on the surface of the moon, there can be significant mobility and travel between, say, one settlement and another settlement. So this can be extremely convenient. There'll be plenty of energy. It'll be easy to build, for example, trains to go from one settlement to another. For the foreseeable future, when you look to other worlds beyond the Earth-Moon system, the distances will still be enormous. So maybe 40 million miles, maybe 100 million miles, 200 million miles. And it just takes a long time to go from Earth to Mars, or from Earth to, for example, the main belt asteroids. The distances are still extremely huge. And so, of course, someday the technology will improve, but the issue is power density. You need a lot of power in order to go from point A to point B quickly, which is why it takes so much more fuel and so much more power for a fast car rather than a modest car.
There is one interesting question. I don't know how it could be spelled. The question is, see, the gravity depends upon the mass of the planet or whatever it is. If a lot of people are going from Earth to Earth to Moon, and if the mass of the Moon increases considerably, will it affect the gravity relation of Moon and Earth?
Yeah, we are not so important compared to the worlds, the Moon, Mars, Earth, Jupiter. We are very, very small players. We are not even ants compared to the worlds. Humans are even smaller than ants, maybe microbes. So no, that any amount of settlement on the Moon would make no difference to the gravitational relationship between the Earth and the Moon.
Yeah, of course, of course. What is the temperature range, highest and lowest on the Moon?
Say that again?
Temperature range, that what is the highest temperature during the daytime and what is the lowest temperature during the night time?
So just like on the Earth, if you go to the poles, the range of temperature is more narrow and it's always fairly cold. And if you go to the equator, you get a huge range of temperature from season to season and from day to night. So on the Moon, the biggest range of temperature occurs on the equator. For example, near where the Apollo landings took place. And there it can be like a plus 200 degrees above 0 Celsius and minus 200 degrees approximately. This is just approximately. At the south pole of the Moon, where we are talking about the ices and the prospective settlement, it is always rather cold, but the peak temperatures are like 30 degrees below 0 Celsius. And the coldest temperatures are maybe 230 degrees below below 0 Celsius. So this sounds quite challenging. However, in fact, it's easier to design systems that are where everything outside is always cold, as opposed to for 2 weeks it is 200 degrees, and for 2 weeks it is minus 200 degrees. So it's actually very challenging to build systems that can deal with this kind of massive thermal variation.
Yeah. The last question.
So cold is cold. Okay.
Yeah, please continue. Please.
I was just going to say, having it be a little bit cold outside all the time makes it easier to design the system, in my opinion.
Yeah. So the last question I would take: how soon or how much later will it be feasible economically, technically, and environmentally to travel to the Moon by a common citizen? Economically, so even today, going from India to USA, it takes minimum $1,000. So how will it be economical to travel to space?
Right. And this is one of the core questions and the core assumption of the studies that we are now doing. So as I mentioned before, only 20 years ago, it was very typical for access to space to be maybe $25,000 per kilogram. And so something like $30 million for a ticket to go to the International Space Station, something like that. Very soon, going into space will be radically cheaper, but it's probably still going to be $1 million to go into space, and several millions of dollars to go to the moon. So it's going to be a long time before an ordinary citizen could travel. So it's more like if you look at the history of transportation on Earth, there is a great span of time and technology between the 19th century, when people traveled on steamships and only the extremely wealthy could travel back and forth between the continents. If ordinary people traveled, they did it once. They did it, to immigrate, to move to a new country. But only the very rich could travel back and forth. Today, with airlines and advanced technology and jet turbines and all of that, ordinary people can afford it. I think that for the next 30, 40, 50 years, we will still be in the period when only the very rich could afford to go back and forth. And ordinary people might go, but they would go only if they could go and stay, because they are not so rich that they could afford to go back and forth.
The space tourism is a hot subject by SpaceX and Blue Origin and other private players. So that space tourism is more attractive to a common man. And they're thinking that, oh, maybe in another 5, 10, 15 years, I will be able to travel to space. But as you told, that it is not going to be that easy and that cheap. So at least in our generation or next generation, it may not be really possible, except for the very, very rich people. So let us hope that things will improve, the technology will improve, and definitely people will have fulfilled their dream of traveling to space. Sir, thank you very, very much for a wonderful presentation and a wonderful question and answer session. So we are really feel blessed by you for our Space Week program. Thank you very much, sir.
My pleasure.
Thank you,
I
sir.
enjoyed it very much. You are welcome.
Okay.
Okay.
Now,
Bye-bye.
the announcement, tomorrow's announcement for tomorrow's program. We have tomorrow, Tuesday, 6th October, we have the same time, 6:30 p.m. to 8 p.m. That is in the evening, which is 6 a.m. morning, early morning in USA, California. Our speaker is also from California, Joseph Bland. He is the president of Sacramento L5 Society, and he is the former president of NSS Chapter Assembly. Please join tomorrow at 6:30. And with a folded hands, our request to the attendees and the viewers, please follow the etiquettes. Do not interfere by voice or by video. Please follow the etiquettes. Thank you very much and good night.
Full stop.